Alrighty, today we're going to go ahead and do 3.1, which is exponential functions. An exponential function is anything that has the variable in the exponent. So this is just saying that b is the base and x is the exponent, and we're going to say that b is positive for now, and x is any real number, so no imaginaries. Here's one cool thing, is if your base is greater than 1, then it's going to be exponential growth. And if your base is between 0 and 1, which means it's a proper fraction, like 1/2 or 3/4, then it's going to represent exponential decay. So how do we go ahead and graph these? First of all, our base is equal to 3 here, so we're going to note that this is exponential growth. So we should be expecting this to go up. So as the x's get larger, so will the y's. That's what growth represents. So anytime you want to graph something and you're not sure, you can start with a table. So I'm going to start with the bottom this time just because it's easier to plug in. So what I'm doing is going 3 squared because the x is in the exponent, which is 9. 3 to the first power would be 3. 3 to the 0 power would be 1. 3 to the negative 1 is 1 over 3 to the first power, which would be 1/3. And then 3 to the negative 2 is going to be 1 over 3 squared, which is 1/9. So in terms of graphing, we normally graph 5 things. So what I'm going to tell you to do with this one is 1/9 is kind of ridiculous to graph. So I'm not going to have you graph that. But there is going to be another thing here because this one's 1/9. And what if I asked you for 3 to the negative 3? That would be 1 over 27. 3 to the negative 4 would be 1 over 81, and so on. So what's happening is as the x's are getting smaller, the y's are starting to get closer and closer to 0, which means we're going to have a horizontal asymptote. So let's just go ahead and plot these points. So negative 1, 1/3, 0, 1, 1, 3, and then 9 is like way up there. And so the graph is like that. And then, like I said, you're going to have this horizontal asymptote. So instead of having 5 points that will define an exponential graph, we're going to do 4 points in its asymptote. And I do want you to label that asymptote just to make sure that you see where it's at. All horizontal lines are y equals 0. So like I said, to completely do these, you need 4 points and an asymptote. So you notice though when you read the problem it just says to graph this, you have to just remember that exponential functions have asymptotes, so you're going to have to put them in there just like rational functions. Okay, example 2, what we're going to do is we are going to take our parent graph, which is 3 to the x, and we are going to shift it around. So we are going to do the same thing we did before. This right here, this 2 is not in with the x, so it's going to be in vertical transformation. So this one's up 2. This one right here is in with the x, and some of you are still doing the opposite, but I really encourage you to set this equal to 0 because we're going to be doing y-axis transformations, and that's going to be a problem if you just do the opposite. So this one's left 4. This one right here, we have a negative out in front. If the negative is out in front, it's a reflection in the x-axis. And then we have x minus 1 equals 0, so we're going to go right 1. And then we're going to go, after we've gone right 1, we have our up 2. And then on this one, because the negative is in with the x, we're going to reflect over the y-axis. And then this is where just doing the opposite doesn't always work because it looks like you might want to go left 2, but if you do the math and divide properly, you're actually going to go right 2. And again, we're going right 2 because it's in with the x. So those are the listings of all the transformations. So what I'm going to do, because this is all the same parent graph, it's all 3 to the x, is I'm going to just put the dots for the parent graph on every single one of these. You can do it one by one if you'd like. I just think our brain remembers the pattern better, so it's just faster for me to do it this way. If you're like, well, what do we do on the test? Well, if you don't remember what the pattern is, you just make a table and figure out where that asymptote is starting at, and then go from there. Okay, so there's all those points for that. And then what we're going to do is we're going to move all the points up 2 in this first graph. So I'm going to use a different colored pen just to make sure it's visible. So remember, originally our asymptote is right here at y equals 0, and if I shift my whole graph up 2, so 1/3 do and 1/3 do, then what's going to happen is, because I did a vertical transformation, the asymptote is also going to shift up 2. And it's going to be y equals 2. So there's that first one. This one right here we're going left for, so I'm going to move every point 1, 2, 3, 4. Now on this one, because I only did a horizontal transformation, guess what? The asymptote is not moving. So that's y equals 0. Moving on to the next one, we have a bunch. So remember that whenever you're doing transformations, a review from 1.6 is that we always take care of stretching and shrinking first. So I'm just going to write that right here. You stretch or shrink first. Okay, and then the next thing you do is reflect. And then the last thing you're going to do is vertical or horizontal transformations. So that's just your friendly reminder for that. So when I get to this one, the first thing I'm going to do is reflect it over the x. So essentially when you reflect over the x, your x values stay the same and your y values change signs. So all of these, this was positive 1, it's reflected to negative 1. So all of them are reflecting over. So there's those 4 points, and then I'm going to take each one and move it right 1 and up 2. You might want to do reflections in a different color just so you don't get lost, but I think this one is one we can handle. So here's the thing, the asymptote still moved up 2 as well, and now look what this graph is doing. It's going like that. Here's another connection you might be picking up. This number right here represents your asymptote. So if you look, there was an asymptote at 2, 2. You're like, wait, the asymptote's at 0, but it's not here. Of course, mathematicians aren't going to write that, but I could write plus 0. Okay, so that's an easy way to see if it's going to move or not. Moving on to this next one, I have a reflection in the y-axis, which means that the y's are going to stay at the same, but the x's are going to flip. So this one is going to come over here. This one will stay the same because it's on the y-axis. This one will flip to this side, and this one right here will flip over here. And then remember, I have to move everything over right 2. Oh, that's funny. That ended up right back on its. Now, I moved it right and I didn't move it up or down, so my horizontal asymptote is staying at y equals 0. So the next problem is just to help us remember how to stretch or shrink our graphs. So we're going to do that one real quick. So this one is going to be a vertical stretch by 2, and I know it's vertical because it's not in with the x. If the 2 was up here, it would be a horizontal stretch or compression, and the way that I would adapt that was I would cut all my x values in half. Remember, we have to, if we were solving for x, we'd have to undo multiplication by 2. Remember, our equation's already solved for y, so whenever you're dealing with y transformations, you don't have to do that. So remember, I'm going to show you 2 different ways first. I'm actually going to make a table, but I'm going to hold off on that. So remember, I'm getting my points on here right now. Those are the points that are from 3 to the x, because that's my parent graph. And I'm acknowledging that I have a vertical stretch by 2, and then I'm going to go down 4. Again, I'm not messing with horizontal because this is not in with the x and neither is the 2 in front. So vertical stretch by 2 means to double all your y values because that's how you would double in the vertical direction. So this was at 1/3, so it would be at 2/3. This is at 1, it jumps to 2. This is at 3, it jumps to 6. This is at 9, it jumps to 18. Okay, so that's a huge jump. So I'm just going to kind of like dot this one so you guys can see that it's just like taking off so much faster than 3 to the x is because it's being doubled. And then the last thing we have to do for that one is move everything down 4. So 1, 2, 3, 4. 1, 2, 3, 4. Make sure you get the right points. 1, 2, 3, 4. And this one I'm just approximating because it's way off my graph, but I'm going to make sure that I keep it because it really shows the pattern of this graph is to increase at a significant rate. Okay, so there's our graph right there. So this is the asymptote y equals -4 because it's a -4. And then just to show you, let's hypothetically say that this is like, you're like, oh my gosh, I can't do this. This makes no sense to me. So even when you do it, this is 3 to the x. This is the equation for, or the table for 3 to the x. If I were to make a table here for 2 times 3 to the x, all this means is like take all your values and double them. So this would be 2/3, this would be 2, this would be 6, and this would be 18, which is exactly what we got. But you can always do the math. If you're like, how did you get those numbers? And I see you just doubled them, but why? Just do this. What's 3 to the -1? It's 1/3 times 2. 2 times 1/3 would be 2/3. And then when you plug in 0, 3 to the 0 power is 1 times 2 is 2, and so on and so forth. Okay? So we just saw an example of exponential growth and we transformed it a bunch. Now what we're going to do is see an example of exponential decay. And I know this is exponential decay because the base is a proper fraction, meaning it's less than 1 but greater than 0. So same thing, you need to make a table for it. So when you plug in -2, you're going to have to, here's the math for that, 1/2 to the -2 equals, you can shower the power here, so that's 1 to the -2 over 2 to the -2, and then you're going to need to flip that because they're negative exponents, and then you'll see that that's just 4. So that's the way you would go about it from there. This is 2, this is 1, this is 1/2, and this is 1/4. Again, the smallest value we're not going to plug in just because we want to do 4 points and an asymptote. And we're just going to plug these in. So -2, 4, -1, 2, 0, 1, 1, 1/2. And you can see the next one would be 1/4, then 1/8. Then 1/16, so this is y equals 0, and you can just try and get both of these in here. As the x's are getting larger, so are the y's. As the x's are getting larger, the y's are getting closer and closer to 0. So you can see that would be decay. It's getting smaller versus growth, it's getting larger. So in example 5, all we're doing is transforming an exponential decay graph. So in your homework you can have 2 to the x, which we don't cover in our lesson, but essentially you're just going to make a table and transform it from there. You guys can definitely pick that up. So here x plus 1 equals 0, x equals -1. I'm going to go left 1 and up 2 for that one, and then this one, because the negative is in with the x, I am going to reflect over the y-axis. And then I'm going to go down 3. Okay, so getting my points on there, again, since my parent function is a graph before transformations, I can take away the numbers that represent the transformation. So it's 1/2 to the x, which we conveniently have right above here. So -2, 4, negative 1, 2, 0, 1, 1, 1/2. I'm going to do the same thing over here. So those are the parent points right there, and we acknowledge that there's an asymptote, but we'll graph that when we do the transformation. So I'm just going to go left 1 and up 2, left 1, up 2, left 1, up 2, left 1, up 2. So here is my graph right there, and that's at y equals 2. And then the next one is going to be reflecting in the y-axis. So remember, that means all the y values stay the same, but the x values change signs, so they just get flipped. So that's what that looks like, and then I got to move everything down 3. And then here's my horizontal asymptote at y equals negative 3, again making the connection with the equation. And there we go. So now that kind of looks like an exponential growth graph, because a reflected decay, a reflection in the y, is an exponential growth. And it has to do with the fact that I can do this mathematically. I can go 1 to the negative x over 2 to the negative x. I can shower that power, which is the same thing as 2 to the x over 1 to the x, which is the same thing as 2 to the x. If you do, or I'll do it like this just so you can see. I can distribute-ish that x, and then it's just 2 to the x. So that was exponential growth. So it's just manipulating. So it's not necessarily, you're like, why isn't that decay? It's just because there's a more simplified form. Generally, we don't leave exponents negative, so there's that. Okay, for the next part of this, we are going to be studying the following table and seeing if it represents exponential growth or exponential decay. So right here we have negative 2 to 4, negative 1 to 2, 0 goes to 1, and so on and so forth. But when we have an exponential growth graph, which we can take a look at example 1 right here, as the x's are getting bigger, the y's are getting larger. So in a table form, we're looking here. As the x's are getting larger, the y's are actually getting smaller. So does this table represent exponential growth? No. Why or why not? Because as x goes to infinity, f of x is going to 0, not going to infinity, which we would expect to see from an exponential growth. Write an exponential equation to model the data. So for you to be able to do this, the two key ones that I want you to look at are anything to the 0 power and anything to the first power, right? So this one right here, this leads me to believe that I should start with 1/2 to the x, because when I plug in 1, I would get 1/2. Then what I'm going to do is look and check it with other points. So start with 0. Anything to the 0 power is 1. And 1/2 squared, so this is my little check right here. So we have 1/2 squared equals 1 squared over 2 squared, which equals 1/4. So this is the equation that we would write right here. Okay? Now, of course, it's going to be just a little bit more difficult in the next problem. It says, does this table represent exponential growth? So you're looking and you're going, okay, this is the direction of the x's are getting larger. Are the y's getting larger? You're like, nope. Why or why not? Same reason. As x's are getting larger, meaning as they're going to infinity, the y values are getting smaller, meaning they're going to 0, not infinity like we would expect them to. So if we try to write an equation that models that data, the first thing we want to check is anything to the first power. So we start there and we're like, okay, a good guess for writing this is 2/3 to the x. When I do f of 1, I get 2/3 to the first power, which equals 2/3, and that checks out. However, when I do f of 0, I get 2/3 to the 0 power, which is 1. That does not work out because when you plug in 0, you're supposed to get 2. So this way is not going to work out. So what do? Well, what are other ways to get that 2 there that would help me out? The key lies in this right here. If I have a vertical stretch by 2, it might look something like that, and this might actually help me out. So if I put the 1 there, 2 times 1/3 to the first power would be 2 times 1/3, which is 2/3, which works out. And if I do f of 0, I get 2 times 1/3 to the 0 power. Order of operations tells us to take care of that first. Anything to the 0 power is 1. That gives me 2. That works out right there. So you're going to know if you're going to have some sort of stretch or shrinkage based upon what is happening when x equals 0. Okay, because if it's not 1, then something is being multiplied by it. So you go from there. So this one is f of x equals 2 parentheses 1/3 to the x. And I just want to pause and make sure you realize you cannot write this as 2/3 to the x because order of operations says we have to take care of exponents first, and we can't. So if there's a variable in the exponent, you cannot multiply those together. Alrighty, let's go ahead and flip it over and see what we have coming up. So example 5 says the graph of the exponential function is right here. What is the value of c, and give a reason? Well, remember we've been talking about c right there. That's that number right there. And if we look back on the other side, we're saying c is our horizontal asymptote. So c equals -3 because there is a horizontal asymptote. At y equals -3. Okay, part B says rewrite the equation using your value of c. So here's our equation, which is y equals a times b to the x plus 1. Do you guys see that left one? Minus 3. Then use f of -1 equals -2 to find the value of a. Okay, so when x is -1, y is 2. So y is 2, don't know a, but x is -1. Oh, they picked that intentionally because even though I have two unknowns, I'm going to be able to simplify this right here. This is -2 equals a times b to the 0 power minus 3. And what is anything to the 0 power? It's going to be 1. So it's -2 equals a times 1 minus 3. Follow your order of operations, which is -2 equals a minus 3, because you're going to multiply before you subtract, and then you're going to add 3 to both sides, and you're going to find that a equals 1. All right, cool. No stretching or shrinking since a is the number before the base. Use another point on the graph to determine the value of b. What is the equation of the picture we're seeing? So you're going to pick another point on the graph, and my favorite point to pick is probably my y-intercept if it's nice and clean. Another point you might want to be able to pick is like 1, 1 because it's going through that, but I'm going to pick the point 0, -1. So there's function notation and there's the point. So right now the equation that we have is that we have 1 times b to the x plus 1 minus 3. At this point, we all acknowledge we don't need that 1 there anymore because 1 times anything is itself. So I'm going to just stop writing the 1 and then plug in the 0. So I get to there. So I have b to the 0 plus 1, which is just b to the 1 minus 3. So then I have add 3 to the other side, so I get b equals 2, and that's just because anything to the first power is just itself, so we don't write it. So it says to write the equation, making sure we follow all of our directions. We have 2 to the x plus 1 minus 3. If you wanted to put times 1 in here just because you want to be super thorough, that's fine. It's just not necessary. Okay, example 6 is actually 1% extra credit if you can do that on your own. So I will be checking that first thing in the morning when I check your notes. So if you can do all of example 6, that's extra credit. We are going to be moving on to E, and this is just more exponential stuff, so that's why it's in this chapter. You're going to need a calculator for this part, so go ahead and grab one. So E, just like pi, is an irrational number. So instead of having to write this over and over again, mathematicians gave it a variable E, which is weird because it's actually not a variable. It's representing a specific number like pi. It's called, the natural base. You can look up why. We use it a lot though, especially with logarithms. So we're going to start with a pretty basic example. The function 6e to the 0.013x describes the world population in billions, x years after 2000, so super important to see what your variable is representing. It's not just the number of years, it's the number of years after 2000, subject to a 1.3% annual growth rate. So if you see there's that growth rate represented in the equation, find the world population in 2050. So x is actually going to represent 50 because 2050 is 50 years after 2000. So all we have to do with this particular problem is plug in 50. And then we're going to plug it into our calculator. So here is my calculator. And you're going to type 6, and then calculators are so smart. I just told you guys that we use this a lot in logarithms. This is the natural log button down here. It says ln. You see e to the x is the shortcut key, so you can hit second and then that natural log button, and that pulls up your e, and then you're going to do 0.013. Always watch your where your decimal place is at, times 50. If you don't have this newer calculator that keeps it up in the exponent till you tell it to arrow over and not keep it up, you should put your exponent in parentheses so it does that math first. We do that and we get 11.493. So there will be 11.493 people. No, this is in billions, so make sure you put your label. There will be 11.493 billion people. Okay? The last part is compound interest formulas. I'm going to tell you, you have to memorize these. You learn these in Algebra 1 or Math 1. You learn them again in Algebra 2 or Math 3. And so at this point, you should be able to memorize these. Okay? So in this first equation, which is a compound interest formula, A is your balance. That's like your total after you've invested. P is your principal. R is your interest rate. You're going to want to make sure that's in decimal form. N is the number of times per year that it's compounded or that your interest is reassessed and you earn money from your interest. So semi-annually is 2 times a year, quarterly is 4, monthly is 12, and then the last one should actually be over here. It's time. T is the number of time, the number of years. So if you see those, there's actually 2 N's in this formula. So we'll go over compounding continuously in a minute. The sum of $10,000 is invested in an annual interest rate of 8%. Find the balance in the account after 5 years, subject to quarterly compounding. So we have A, P, So what I'm doing is just listing the variables in my equation. So I'm using the first one because it says quarterly compounding. The only time I use the second equation if it says continuous compounding. So quarterly would mean 4 times per year. So that's n is the number of times per year. The rate is going to be 0.08. I'm going to subject it to 5 years. It's a sum, initial sum, or as of 10,000. And I'm solving for A. So one unknown means I can do that. And you're literally just plugging in and then making sure you plug it into your calculator properly. So I have 10,000 times 1 plus 0.08 divided by 4 raised to the 20th power if you multiply those together. And so after 5 years, the person has made almost $15,000. I will say in money we round to cents, so make sure you round to the hundreds position. All right, last problem right here. Continuous compounding is this formula right here. You don't need as much stuff. It's A equals PERT. Right there just spells PERT, and the R and the T are in the exponent. So A, P, R, T, because E doesn't represent a variable in this situation. So it's the same amount of money invested at the same rate, at the same amount of time, and plug that in. Don't forget the E to the RT, 0.08 times 5, and then into our calculator we go. And we get that we are going to make slightly more money by continuously compounding than by compounding quarterly. If you don't know what that means, then you just Google it and it'll give you a quick rundown on the difference between the two. Alrighty, that's it for today. Have a good one.